We're now going to go on to talking about acids and bases. So we want to consider the concept of the Arrhenius acids and bases. And so this is discussing how that we have dissociation of acids and bases in solution. So I believe you probably would not have covered this yet in class, or you may have only have just begun to learn this. So I accept that this is a relatively new concept, but I am showing you this so that you have some preparation for these concepts which are to come, and so that you are hopefully well prepared for this topic. And so in aqueous solution, acids will dissociate. So acids are going to dissociate to form hydrogen ions, which we can otherwise call protons, and anions. And so the more dissociation, the greater the strength of the acid will be. So for example, if we consider a strong acid like HCl, in water, we know that HCl can dissociate and lose a hydrogen atom to the water, and so the water will gain an electron to form H3O+, which is characteristic of an acid. So acids will form H3O+, or H+, and then we'll have left behind the chlorine ion. And so this can also be written as HCl dissociates into H+ and Cl-. And so this is just showing that it has full dissociation because it is a strong acid. But when we consider bases, they're going to do the exact same thing. So bases, except forming hydroxide ions. So bases are going to form hydroxide ions when dissolved in water because they can either dissociate due to containing the hydroxide ion. So for example, sodium hydroxide, which is a very strong base, can dissociate into Na+ and OH-, and so the OH- is what is characteristic of a basic solution. So it has that OH- because it is basic. Or they can react with water to accept a proton, which then produces the hydroxide ions. So for example, if we had NH3 and we added that to water, we would then get NH4+, which is ammonium ion, plus OH-, and so that OH- would be the leftover from water. And so then that, because we have the OH- present, it's showing that we have the hydroxide ion being produced. And so ammonia, or NH3, is a weak base, and so it does not have a full extent of dissociation. So that's why we can see that we have a reversible arrow for the ammonia reaction, where the water is accepting a proton, because the reaction can be reversed to go back the other way because we don't have full extent of dissociation. Whereas if we're considering the sodium hydroxide, that has full dissociation because sodium hydroxide is a strong base. And so when we consider the strength of acids and bases, we need to consider this concept of strong and weak versus concentrated versus dilute. So we can have strong acids, and you may think a strong acid is the same as a concentrated acid. But as a matter of fact, they are very different, because strength of an acid and base is going to relate to the proportion of dissociation. So the amount at which those atoms have split. So for example, the hydrogen chloride ions or the hydrochloric acid ions, or HCl, have split into H+ and Cl-. And so a strong acid or base is going to have a greater extent of dissociation. So for example, HCl is going to mostly split into H+ and Cl-, in aqueous solution. Whereas if we compare that with something like ethanoic acid, which is a very weak acid, we can see in this diagram here, we have a very limited extent of dissociation. So most of the ethanoic acid molecules will remain as the original ethanoic acid molecules in solution, and very few will split into the CH3COO- ion and the H+ ion. Then when we consider concentration of acids and bases, and we consider concentrated versus dilute, concentration is going to refer to how much of the original substance is going to be dissolved in the aqueous solution. So if we have a lot of the acid molecules in the solution, regardless of whether it's a strong acid or a weak acid, we can see like this one here on the right at the bottom, we've got a concentrated solution because there is lots of these molecules of the acid, regardless of whether it's a strong or weak acid, there's lots of them in that solution. Whereas a dilute solution, we have very few of those acid molecules in the solution, or base molecules in the solution. And so that's going to mean that because there's so few of them, we consider it to be dilute. So that's just something very important to consider when talking about the properties of our acids and bases and knowing what a strong acid or a strong base is. So now we want to talk about the self-ionization of water, because water spontaneously self-ionizes to a very minor degree. And so this is because hydrogen ions associate with water molecules to yield what we call hydronium ions. And so hydronium ions can act as a protein donor, whilst hydroxide ions remain free in solution. And so acidic or basic solutions will rapidly increase this degree of ionization. So when acidic and basic solutions combine, the hydroxide and hydrogen ions yield to water and the solution neutralizes. So this often yields a salt as a product. So we can see our equation here. We've got H2O plus H2O, so basically water plus water is going to produce hydronium and hydroxide. And so at 25 degrees Celsius, or at our STP temperature, the number or the proportion of hydroxide ions is going to be equal to the proportion of hydronium ions, and so that's going to equal to 1 times 10 to the power of minus 7 molar. And so that can help us determine concentrations of hydroxide ions and concentrations of hydronium ions in order to determine concentrations of our acids and bases. So when we look at the pH scale, pH is going to be a measure of how acidic or basic a solution is. And so pH is the negative logarithm, so in base 10, of the hydrogen ion or hydronium ion concentration. So we can consider it to be pH equals the negative log of the concentration of H+, or pH equals negative log of the concentration of H3O+. Whereas we also have this concept of POH. And so POH is the negative logarithm in base 10 of the hydroxide ion concentration. And so that's going to be our OH minus ions. And so the formula for POH will be POH equals negative log of the hydroxide ion concentration of the solution. And so as the hydroxide and hydrogen ions associate to yield water, and the formulas can then be used interchangeably. So the maximum we have is 14 and the lowest being 1. So the maximum 14 is representing the lowest hydronium ion concentration when we're looking at pH, when we're looking at POH, and so the formulas can then be used interchangeably. So in any solution at 25 degrees Celsius, H3O plus times by OH minus will equal 1 times 10 to the power of minus 14. So we can also use that to determine concentrations of hydroxide ions and hydronium ions at 25 degrees Celsius if we don't know the concentration of one, but we know the concentration of another. And so this can help us convert between pH and pOH. We also have these formulas of pH equals 14 minus pOH and pOH equals 14 minus pH, which just helps us to easily convert between these. We also have some important reactions of acids which we need to consider. And so these are very important to remember. And also an important note is that salt is considered to be any ionic substance. So any ionic substance which is produced in a reaction is considered to be a type of salt. So our first reaction which we have is acids react with most metals to produce salt and hydrogen gas. So that will be 2HCl, as an example, 2HCl plus Mg, so magnesium, is going to make magnesium chloride and hydrogen gas. So that's where the acid is hydrochloric acid, the metal is magnesium metal, the magnesium chloride is the salt, and the hydrogen gas is obviously the hydrogen gas. We next can have acids react with metal hydroxides, so bases, to produce salt and water. And so this is known as a neutralization reaction because the acid is being neutralized by the base, or the base is being neutralized by the acid, and so they cancel each other out. And so an example of this is hydrochloric acid plus magnesium hydroxide makes magnesium chloride and water. And so in this case, the acid is the hydrochloric acid, the base or metal hydroxide is the magnesium hydroxide, and then the salt is the magnesium chloride. And then of course we have water produced as well. Finally, we have acids reacting with metal carbonates, and this produces salt, water, and carbon dioxide. And so an important thing to note about this reaction is that it produces carbon dioxide, and so you will notice gas and bubbles being produced if you conduct one of these reactions. And so an example of this is if we have hydrochloric acid and magnesium carbonate, and we can combine those to make magnesium chloride, water, and carbon dioxide. And so this is where hydrochloric acid is the acid, magnesium carbonate is our metal carbonate, magnesium chloride will be the salt, and then we've got water and carbon dioxide.